Hello, welcome to the Engineers channel. Today we are going to analyze the deflection of a cantilever beam. This is a topic that every engineer must master. Every engineer must know where and how the equation of a cantilever beam is derived. Although this is already in the tables and we use the equation from the tables, so the exercise tells us for the cantilever beam AB with a uniform cross-section that supports a load P here at its end at point A, find the elastic equation of the beam. Also find the deflection and the slope at point A. And graphically, it is as follows. Look, when I load the beam here at the end, my beam will curve due to the deflection, and this end A will descend a certain amount. That amount is called the deflection. It needs to be calculated. But when a curve is generated, this curve has a certain slope, a certain inclination here at point A. We also need to calculate the slope equation. So we are going to calculate what the slope is here, what the deflection is, and we are going to find the elastic equation of this curve. It is a quite basic exercise, so the first step we are going to take is to make a cut on this beam at a distance x. And there it is. We cut here a distance x from end A, and we are going to extract the internal loads that are acting here at this cut. This is our cut. These are the internal loads. There is a shear. Since I took the left side of my beam, it is already established by convention that when you take the left side, the shear is drawn downward and the bending moment is drawn counterclockwise. Setialas. And these are the internal loads that this point of the beam is supporting here. Now we are going to derive the equation, and then we will sum the moments with respect to the cut, that is, with respect to this point, sum the moments with respect to that cut point, and that sum of moments must be equal to zeros. The first moment is produced by the load P, and the value will be P times this distance, x. So we will put here P times x and the direction of rotation of that moment. Notice we rotate around the cut as the load goes down. It will be counterclockwise. Counterclockwise is positive. Done. The next moment is this internal moment m. So it is also counterclockwise, so it will be plus m. The load V does not generate a moment because it is on the cut. Then I close the equation by setting it equal to 0. If I mirror the internal moment here, the internal moment will be minus P times x. And from this moment, from the value of the moment, we go to the differential equation. And this is the differential equation for the moment in x, second derivative of the elastic curve with respect to x squared times the modulus of elasticity times the moment of inertia equals the moment in x. I replace this moment in x. It turns out to be this. I replace it, and there is my differential equation. But I already replaced the moment value with negative P times x. Next, what we do is integrate both sides of the equation with respect to x. Note, this analysis is E times I is constant because the cross-section and the material are uniform. P is constant because it is the load here at the end and it does not change. Since they are constants, I will take them out of the integral and perform the integration. And there is the integration. Remember that? This is an indefinite integral. Ready? So since it is indefinite, I must add here to the process of integration. Remember that the integral of minus p comes out of the integral. The integral of x to the 1 is x squared over 2, plus the integration constant because it is an indefinite integral, indefinite for not having boundaries. But now we are going to analyze the boundary conditions. At this point, the boundary conditions are always analyzed to determine the value of this constant one. Constant of integration. So the boundary conditions we must see are of y and of x. Of y and of x is the same theta x, which refers to the slope of the tangent line, and what we are going to find out is the value of this slope at point B. So if I come here to the graph and position myself at point B, remember that point B is at a distance x equal to L, right? it's at the end. I'm measuring from here as the reference, and we move L and reach point B. So he's at this point, is I'm going to draw the slope of the tangent line. It will be this one. Look, this red one that we just marked. What is the slope of the tangent line to the curve at B? 0. So we are going to say that at point B, where x equals L, the slope at B is 0. There it is. And now, since the slope is 0, I replace this slope with 0. Obviously, all of this becomes 0. So, what will we have left? 0 equals negative p minus p times L squared, because x equals L. Remember, I replace x with L. So, L squared over 2 plus C1. And from here, what we do is solve for constant 1. How? We move this to the other side, and then that constant 1, C1, will be p times length squared over 2. And there, the integration constant is determined. What I do now is replace that constant here, and I will have the equation. Note the slope equation, and there it is. This is our slope equation. Now, from this same equation, but remember that this theta x is the same as y of x. And there it is. We are going to integrate it again on both sides, and we will integrate with respect to x, and exactly the same thing will happen. The integral of the first derivative gives us the antiderivative. It is called that in mathematics the antiderivative, or the original function, and of x by e by I. Because e and I are constants, then by e by I, now we do the integration process. So here we will have minus p over 2. This, the integral of x squared, will be x cubed over 3. But I can multiply this 2 with this 3, and then I will have px cubed over 6, p times x cubed over 6, done, plus p is constant, it comes out of the integral, L is constant, it comes out of the integral over 2, and I will have it by dx, whose integral is x plus an integration constant 2, because it is an indefinite integral. And again, we need to determine the value of the second integration constant. So we go to the boundary conditions, but we are going to evaluate the deflection here. Then, the deflection, where we are going to evaluate it at B, that is at the fixed support here. How much is the deflection there? So here we are at a distance L from A. We are at L at a distance L. And there the deflection is 0. Because this point is fixed, so it does not descend. It does not descend like point A does. So I substitute this condition here in my equation, and there is the result. When I replace this deflection with 0, all of this becomes 0. Here, the x times L gives me L cubed. Here, x times L, L times L squared, L cubed. Notice that these are similar terms. I can simplify them and solve for C2. By solving for C2, we find that C2 is equal to negative 1/3 of p times L cubed. And then, pues el siguiente, we have determined this integration constant, then we replace it here, and we will have the general equation for the elastic curve. And there is our equation. It is known as the elastic curve equation, or the equation of the elastic curve. Now, since the exercise also asks us for the deflection at point A and the slope at point A, what we do is substitute here in these two equations. We will substitute in this equation the slope equation, and in the deflection equation. And we are going to replace the values of x here and here. The same here, the value of x. By what are we going to replace them? They tell me if it is at point A, x is 0, because here is the origin of the reference. Look, x, y, 0, 0 is here, so A is at 0. So the x times 0, by making that replacement, we will find that the slope is p times L squared over 12ci, and that the maximum deflection, replacing all this with 0, since it all becomes 0, will be minus pl cubed over 3a, And these are simply going to be the maximums because when analyzing the curve, this is the most deflected part of the curve, the lowest point, and this is the one with the greatest slope, right? If I approach point P, this slope keeps decreasing and this deflection keeps decreasing until here it becomes 0. And so these are the equations that appear in the tables. You find the slope equation and the deflection equation. I invite you to subscribe to the channel, to share this material with colleagues and friends so we can continue creating more content. And remember, if you liked the video, give it a like. See you in the next video.